Hello everybody. This video will deal with our satellite. The satellite is the Cape 2 satellite, and it will be the second satellite in a series of satellites from the University of Louisiana. So let's start describing our satellite. We start with our solar panels here, and these guys are triple junction solar panels that have 28% efficiency. There is essentially 14 surfaces, and each surface contains 2 cells in series. They produce about 4 volts at maybe an amp in full sun. Each panel, only about 1 panel or 1.5 panels will ever be illuminated at any one time. So these panels are connected to what we call our always-on bus. And here's what happens is when we get ejected from the satellite, this separation switch closes. This goes to our watchdog timer, which actually now closes our circuit to 3 things. One is the 3.3 volt bus, which powers all the PICs on the satellite. We need a 5 volt bus to run one of our radios, so this is a up converter from 3.3 volts roughly to 5 volts, and we have what we call an unregulated bus, which just varies with the available voltages in batteries. In addition to the solar panels, we actually are flying 3 lithium polymer batteries. That gives us a combined battery capacity of about 30 watt-hours. I want to back up and say something about the solar panels. Is that our solar panels, will fully illuminated, will produce about 2 watt-hours per orbit. If we're lucky, we may, depending on the orbits and things like that, we actually might get as much as 4 watt-hours per orbit. So now let me shift and start talking about the radios and payloads. So let me get over here to the UHF section, and we are flying essentially 2 UHF radios. One is a UHF transceiver. It turns out that this transceiver is a CC1101 produced by TI, and we have a software-defined radio which is produced by the students at UL. So let's quickly go through this thing. Is that let's take the radio. This transceiver is a single chip. Comes through a switch to a gain block, which takes us from roughly, say maybe 0 dBm to plus 10 dBm, and then we come into a high power amplifier, which will get us to 1 watt. And we go through a solid state switch to our UHF antenna, and if we're lucky, this antenna will have virtually 0 dB gain in almost any attitude of the satellite. If we're running the SDR transceiver, it comes through this switch to the gain block to the high power amplifier and out to our antenna. One of the sensors that we're checking on our high power amplifier is the temperature of the high power amplifier, and this is connected to our unregulated bus. And when this amplifier is on, the solar panels are not sufficient to power this amplifier, so we will be pulling power from our batteries. In the receive direction, our antenna comes in from the receiver to a low noise amplifier. It's got a noise figure of less than 2 dB, and perhaps as we go through the satellite, we'll actually get it closer to under 1 dB. We then pass through a bandpass filter, and this is then switched through solid state switches either to our onboard transceiver or to the SDR. So let's move on and start talking about the VHF side. So let me bring up the VHF schematic. And this is our VHF schematic. And we have several payloads on board. We have a TNC, which allows us to talk to our ground stations via AX25 protocol. This runs at 1200 baud and is a protocol that's widely accepted by the satellite and amateur community. In addition, we have a text-to-speech payload where we can actually take, communicate and store text or from the ground station, load text commands into our text-to-speech, and this will be transmitted out on our radio. We also have a parrot repeater where we will listen for approximately 30 seconds to our receiver, and we will then play that back in simplex back on our transmitter. We in addition have a touch-tone receiver on board. So let's trace some of these paths through the satellite. So let's start with the receiver side. Is that we can receive commands from our ground station via this thing, and this is our push-to-talk switch, and this will come into our VHF receiver, and our VHF receiver is connected to all four of these payloads. So we can actually command this satellite via this TNC command. We can receive data, for our parrot repeater, and we can receive DTMF commands and instructions via DTMF. On the transmit side, all of these payloads are muxed up to our transmitter through this essentially audio switch to a 300 milliwatt VHF transceiver, which will be operated on 145.825 megahertz. We have an option of going low power or high power. If we take the low power option, the signal will progress through this switch directly to the antenna. If we choose to, if we choose to, we can run high power, which we will be connected through this switch to a 1 watt amplifier to this switch. At 1 watt at this frequency, a ground station with a simple handheld rubber duck antenna should be able to adequately hear our satellite. If we choose to run in the low power mode, the 300 milliwatt mode, you can with a very modest gain antenna on the ground be able to hear our satellite. Here are the sensors we're collecting. We're actually collecting RF output on both the UHF and VHF. We have the received signal strength indicators on both the UHF and VHF transmitters. In addition to that, we have temperature sensors on both our amplifiers, and we're monitoring the RF on out of both radios. So basically, that is the makeup of our satellite.